In this next video, I introduce the concept of functional groups, which are very critical for understanding the reactivity of organic compounds, as well as how organic compounds can join together to form more complex molecules. So a functional group is, in essence, just a very specific bonding pattern that we will see in organic molecules. And by bonding pattern, I simply mean the way that some atoms are joined to other ones. As I mentioned just a moment ago, a lot of the importance of functional groups stems from the fact that knowing how one particular functional group reacts tells us a lot about how related compounds will react. And we're not going to really focus on compounds that contain two or more functional groups at this point in time. I might give you compounds that contain more than one functional group just so that you can identify the groups, but we won't learn how to name them or compare how they would react in different circumstances. So first of all, we're going to start off with the groups that fall under the hydrocarbon umbrella. Remember, hydrocarbon means compounds that contain only carbon and hydrogen. So the first group of compounds we will talk about are called alkanes. Alkanes contain only single bonds between carbon. Because they're hydrocarbons, they can only contain carbon and hydrogen. And of the groups that we're going to talk about, alkanes are the only group which are not considered to be true functional groups. If anything, they are considered the absence of a functional group. Alkenes, so you'll notice there's only a one-letter difference there, contain at least one carbon-carbon double bond in the structure. Again, changing just one letter here, alkynes contain a carbon-carbon triple bond in their structure. And then finally, we have aromatic compounds. Aromatic compounds contain a benzene ring in their structure. For reasons that will become clear in Chapter 11, aromatic compounds are not considered to be alkenes, even though they do contain carbon-carbon double bonds, at least as represented in the structure shown right here. So here is an example of all four of these groups. So an alkane, which again is not really considered a functional group, an alkene, which has a carbon-carbon double bond, an alkyne with its carbon-carbon triple bond, and an aromatic compound here, which contains its benzene ring here. Now, we do not consider this to be an alkane and aromatic. Some people might say, well, you've got a CH3 there. Isn't that like the alkane? No. We're just looking for specific patterns here, and so this pattern identifies with aromatic compounds. Alkyl halides are any compounds which contain a bond between carbon and a halogen. And recall, the halogens are the elements from group 7A of the periodic table. They are fluorine, chlorine, bromine, and iodine. Recall that halogens only make one bond, so we see here a bond between what's going to be called an R group and the halogen. Now, in organic chemistry, we like to use R a lot. It's kind of like in algebra what X does. In X is a variable, so R can be a variable, so to speak. And it stands for a group of carbon and hydrogen atoms. So the most common R group you're going to see in a moment is called the methyl group. It's CH3. And then we have this group here, CH3CH2, which we'll see is called an ethyl group later on. So let's take a look at some actual examples. So you'll notice that all of these are alkyl halides, and specifically they're called alkyl chlorides because all of them contain a chlorine atom in their structure. The R group over here is the CH3, called a methyl group. The R group here is much larger. It's everything that contains carbon and hydrogens, and that's actually going to be called an isobutyl group. And then finally we have a large ring here acting as an R group. That's called a cyclopentyl group. You don't need to know any of those names just now. I'm sure that the word alcohol is already familiar to you, so let's get more specific as to what that means. An alcohol is any organic compound that contains an OH group bonded to a carbon. You'll see in a minute that that carbon cannot also have a bond to another oxygen on it. It just has to be bonded to the one OH group. So we symbolize those with R, which again can stand for any carbon-hydrogen group, bonded to OH. So an example here would be this compound here, which is isopropyl alcohol, or common rubbing alcohol. You'll notice again the carbon to oxygen bond, and there is a single bond here between oxygen and hydrogen. Recall, oxygen makes 2 bonds. The next functional group is made up of what we call ethers, and ethers also contain oxygen, and the oxygen atom acts as a bridge between 2 R groups. So these R groups could be the same, or they might be different. So this might be a CH3, and this being a CH3, or this could be a ring, like a benzene ring, for example, and this could be another CH3, so they don't have to be the same. A thiol is similar to an alcohol in terms of its structure, except it has a sulfur in place of an oxygen atom. We'll see that these compounds are known for being very unpleasant in their smells. And amines are compounds which contain bonds of nitrogen to at least 1 carbon. So you'll see right here this is called a primary amine because there is a bond between nitrogen and 1 carbon. This is a secondary amine. It's bonded to 2 carbons, represented by R groups. And this is going to be called a tertiary amine because the nitrogen is bonded to 3 carbons. Remember, nitrogen always makes 3 bonds and has a lone pair. An aldehyde is a compound that has a carbon double bonded to oxygen, and that carbon must be bonded to at least 1 hydrogen as well. So technically, the aldehyde group here is this group of atoms right here. Now, it is possible on this side to have a hydrogen. There is only one compound which has that pattern, and that compound is called formaldehyde. That's probably a familiar term to you. But there are many other aldehydes out there. For example, if we have here a CH3 group, we'll see that that's called acetaldehyde. There's other compounds, benzaldehyde, when there's a benzene ring right there as well. Very closely related to aldehydes are ketones. You'll notice the only difference between an aldehyde and a ketone is that the carbon, which is double bonded to the oxygen, must have a carbon on either side. So neither of these can be hydrogen atoms. These R groups can be the same, or they can be different. And you'll also notice that all of the remaining groups that we'll talk about have carbon double bonds to oxygen. Carboxylic acids contain that carbon double bond to oxygen, and they are also bonded to an oxygen with a hydrogen. Now, a very common mistake that students make at this point is to think of carboxylic acids as also being alcohols, but they are not. The two groups are definitely distinct here. So the important part of a carboxylic acid is this right here, and you'll notice that it contains 4 atoms. So this oxygen, this carbon, this oxygen, and this hydrogen in their grouping. An ester is quite similar in structure to a carboxylic acid. The only difference between an ester and a carboxylic acid is that instead of being bonded to a hydrogen, this oxygen here is bonded to a carbon-containing group. So these are our 4 atoms that constitute an ester. It is important not to confuse esters with ethers. There's two ways that that's commonly done. First of all, the word ester and ether look very similar. They're both five-letter words, ester and ether. Both end in ER and both start with E. But they are definitely different compounds. They have quite different properties. And the other reason that people sometimes confuse them is because you see that there is a carbon-oxygen-carbon bond, just like ethers have. But with the presence of this double bond oxygen, that means it's going to have a considerably different reactivity than an ether. So esters are not ethers. And then the final group that we're going to look at here are called amides. And we have to be careful here not to confuse amides with amines, even though they're only one letter in difference. They both contain nitrogens bonded to carbon. But again, you'll notice that the big difference here is that oxygen double bonded to carbon that we have. That nitrogen can be bonded to just the one carbon, or it can be bonded to two carbons or three carbons. So these hydrogens can be replaced with carbons right there. Your textbook contains 3 tables which summarize the different functional groups. So the functional groups here, the first category is hydrocarbons. Now, the book says that the functional groups here are carbon-carbon double bond, carbon-carbon triple bond, benzene ring. Those are the different structures that you're looking for. But the terms, if you're asked to label functional groups, the terms that you're looking for are going to be these words right here. So the word alkene, the word alkyne, aromatic compound from table 10.3. Table 10.4 shows all of the functional groups which have a single bond between a carbon and a heteroatom here. So again, the functional groups terms that you're going to be looking for are these terms over here: alkyl halide, alcohol, ether, amine, and thiol. The word hydroxyl group is not the term that you want to use to identify an alcohol. I just want you to call those alcohols. So for the time being, it's not important to learn, for example, that a sulfur hydrogen is called a sulfhydryl group. I'll never use that term at all in this class. And finally, we have the functional groups which contain carbon-oxygen double bonds. And so the terms to know from here are aldehyde, ketone, carboxylic acid, ester, and amide. And it's important that you be able to identify these different groups within an actual example. Let's practice our identification of functional groups. I'm going to draw several different compounds, and I want you to copy these down by hand. And I want you to then circle, if possible, or just draw an arrow if circling is not really possible, but in some way identify the functional groups and label them. So for example, if you see a carbon-carbon double bond and it's not in a benzene ring, you would call that an alkene. If you see a carbon bonded to nitrogen and that carbon is also not bonded to oxygen, then that's going to be an amine. You'll want to practice with that table from the book in front of you, the 3 tables we just saw, and eventually you want to get to a point where you can identify these by sight. It helps to make flashcards for learning these different functional groups, and it helps also to practice just by kind of maybe going out on the internet and typing in different functional group terms and seeing what examples come out of it so that you can learn to identify the functional groups in picture examples that you see. I'm going to draw 6 molecules. I'm not going to narrate too much so you can focus on the drawing. the left side of that structure was kind of messy, so let's see if we can fix that. So I'm going to erase some of those atoms. Try to make it clear that it's a hexagon with a double bond there on the left. And now you want to pause the video as soon as this is done drawing and identify the groups. Here we are identifying the first functional group. So that is a ketone, the carbon double bonded to oxygen, and that carbon is bonded to a carbon on either side. That is a six-membered ring with alternating double and single bonds. So that is a benzene ring, which we will call an aromatic compound. That's the name of that functional group. Then we have the carbons bonded to nitrogen. That is called an amine. In the next molecule, we have a thiol, carbon bonded to sulfur bonded to hydrogen. In the next molecule, we have a carbon-carbon triple bond. That's called an alkyne. And then finally, what is probably the most difficult group for many students to identify, we have an ester, oxygen bridging two carbons, and a double bond carbon-oxygen. I'm going to draw a few more molecules now, focusing more on skeletal structures, and I'll draw some molecules that contain two or more functional groups in some cases. As before, you'll now want to pause the video and label all of the functional groups in these molecules. The molecule on the top on the left has two functional groups. We have an alkene, and then we have an alcohol. This next molecule has a carbon-chlorine bond. That is an alkyl halide, and notice that the lone pairs have been left out. That's certainly common. The next group is a little trickier to see. So we have that corner carbon bonded to oxygen, bonded to that CH3. That is an ether. The next molecule has only one functional group, and that is a carboxylic acid. Again, even though this has an OH in it, it is not considered to be an alcohol. Going to the bottom row, we have two functional groups. We have what we call an aromatic group or aromatic compound. And that is bonded to an aldehyde group. Now, the next molecule, many people will incorrectly label as aromatic. They see a six-membered ring and say, oh, that's aromatic. No, it's not. Remember, to be an aromatic compound, it has to have the six-membered ring and the alternating patterns of double bond, single bond, double bond, single bond all the way around. We have a carbon bonded to bromine, which is another halogen, so that makes this an alkyl halide, specifically an alkyl bromide. And we see right there we have a carbon, and even though they're not labeled, they're not required to be, that makes up a ketone. The next molecule is probably the trickiest. So right there, that's a carbon with two hydrogens. Off to the left is a carbon with two hydrogens. So that bridge between the oxygen bridge between the two carbons makes up an ether. And then finally, one more compound. We have a carbon right there, double bonded to oxygen, bonded to a nitrogen. That is called an amide. That is the end of this second video.